Like, do I want to study?
Today, you guys are going to do an exploration. Today, you guys are going to do an exploration where, if you can't, all right, listen, if you hear the sound of my voice, please stop using your own just for the moment. If you can't see this from where you're sitting, okay, move yourself so you can see both of these cards in this track. All right, you can stand up and move around the classroom. All right, so here's how this works. What we have here is we have two carts with the hoops on the front, and the hoops are going to act like springs. And so if I send this card in and it hits this one, okay? Which applies more force, the moving on the stationary or the stationary back on the moving?
Same force.
How do you know?
Because that's Newton's third law.
Good. That is Newton's third law, right?
Equal it out.
Now, what if basically I'm going to double the mass of this one here. If I double the mass and now I send it in, now which applies more force?
Same force.
Still the same?
Yeah.
Are you sure?
Yeah.
How do you know?
Because Newton's third law.
That's the law, okay? What's interesting about this, though, is if you watch this one come in, when they have the same mass, what do you notice about the original one?
It stops.
It stops, and the other one moves off, right? How do you think the speed of the moving one compares to the speed of the original one?
Same speed. Oh, no.
Right.
It's gonna be more.
Does your gut have a sense they might be the same?
No.
More.
Maybe. Maybe. If I put more mass in this one here, if I add more mass to it, what do you know about mass? What does it do to the object's resistance to change in motion?
Increases it?
It increases it, right? So we know that a moment ago, when I sent this in, they were the same mass, it came to a stop. What do you think it's going to do now?
Keep moving.
You think it's going to keep going even after the collision?
Yeah.
Mm-hmm. Just with a smaller speed.
Why don't you try it?
Does it keep moving?
Yep.
Yeah, and we're going to actually exploit that today. What's interesting to me is if you send this one in and it hits the more massive one, this one actually ends up moving back, which I think is pretty cool. So here's what you guys are going to do today. This is called a bouncy collision, where literally they hit and one bounces off the other. Is that cool?
Yeah.
All right. So we got that. Let's diagram it up and see what the diagram looks like. All right. So these are bouncy collisions.
I saw it stop here.
All right. So draw along with me, please. So we have the cart. We're going to put a mass in the back of this one.
It's like, oh, God, that's not good.
We're going to give it a push. It's going to be moving to the right.
Okay, I'm just going to put it away, right?
Now, it's going to contact, now I'm using the little springs because you can't really draw the hoops. It's going to contact this car initially at rest. Is this the demonstration you saw?
Should we be drawing this too?
Yes, please.
Okay.
You always draw things that you draw.
Well, sometimes we don't.
Well, there was that, and when I said please draw along with me, all those, all those indicators.
Sorry.
We're gonna call these car 1 and car 2.
Don't say silly. That's not what I say. Exactly.
I get that.
Yeah, you do.
This arm did yesterday.
Oh my God, do you know who was, yesterday?
All right. You guys ready? So this is the situation. So the original car number 1, hits, applies a force. This force lasts for some time. What happens to the speed of car 1? This is the before picture, and this is the after picture. Going from before to after, what happens to the speed of car 1?
Oh, there's an after picture.
That's the after.
So what's happening there?
This is
after
before.
they've collided?
After they collided.
Speed slows down.
All right, so the speed decreases. So what would you say about its momentum? If you compared its momentum before to the momentum after, what would you notice?
Same?
Slows down.
So it slows down, okay? So what happened to its momentum? Do you guys remember what the momentum is?
No. Momentum is
Mass times.
mass times velocity.
Mav.
Well, it's just it's the straight up momentum, not the change in momentum. So it's the so if it slows down, what happened to its momentum? What happened to the momentum?
Slows down.
So the velocity went down, therefore we would say the momentum decreased. Okay? You okay with that? What about car 2? Between the before and after, what happened to car 2's momentum? Well, what's true about the momentum of car 2 before the collision?
0.
It's 0. Does it have some momentum after?
Yeah.
Yes, it does. So if it went from 0 to some number, would you say it increased? Okay. So implicit in this description is the question, how does the loss of momentum of car 1 compare to the gain in momentum of car 2? Check your neighbor now. See what your neighbor thinks. How does the loss...
Momentum is like transfer.
That's the question. Check with your neighbor.
Because it's always
All right. So, this is the question, okay? This is the question. We saw that car 1 lost some momentum because it slowed down. We saw that car 2 gained momentum because it speed up.
Yep.
How do you think the gain of one compares to the loss of the other?
Energy transfer.
So we're talking about momentum today. What is energy?
Okay, momentum is a form of energy.
Momentum is a form of energy? What is energy?
I never said it was a force. I said it was energy.
What's energy?
Like, you want the definition?
If you have one, I would love one.
Yeah, I do. Can I get one? I actually have a definition.
energy is
Wait, no, like, dead serious, I have a definition.
All right, so the classic definition for energy is it's the ability to do work.
Oh, I was close.
So that's
Oh yeah, I think that's it.
But
What is
then-
energy? Definition. Energy is the ability to do work.
Right, but I have to know then,
Nice.
but I need to know what work is. Because if you're going to tell me the definition of one thing is another thing, and then,
Work equals change in energy.
yeah, exactly. So listen to the words here. We say that, get this is my favorite. Energy is the ability to do work, but work is the change in energy. Does that help us know what either of those things are?
Yeah.
No, it's literally the circular definitions.
Energy transformation?
So-
Wait, what if I found the definition of work? Work is
It's the transfer of energy. I know.
the amount of energy transferred to an object by a force applied over a displacement.
So again, work is energy, and energy is work.
Work is a scalar quantity Both force and displacement are vectors.
Before one.
Brandon, this is crystal clear, man.
This is what?
It's crystal clear.
Isn't it? I guess Canada, they don't like to teach you all those things.
All right, gentlemen, ladies, reset please so we can do today's activity. I want to get into the lab, but we got to do the pre-lab first.
So did this help or not?
No. I like it though. What we want to calculate the momentum of an object, you need to know two things. You need to know its mass and you need to know its velocity. You are going to use the triple beam balances at the stations to figure out the mass of each of the objects. Is that cool? They should be, I mean, the cart by itself should be around 5,500, oh no, sorry, 550 grams, so 0.55 kilograms, but measure so you can be precise. Okay? Car 1 and car 2. Now, how are we going to get the velocities? So what we're going to do is we're going to put motion sensors.
Longer pro.
Yeah, we're going to use the motion sensors over here. We're going to put one motion sensor at this end. Okay? And we're going to put another motion sensor at the other end. Okay? So that we can actually track the motion of each of the cars. Okay? Okay. Now, this is a little challenging. All right, so dig in tight on this one. This motion sensor can only see this car. It can't see the car behind it. So when you push this motion sensor is going to pick up the motion of this car. It's moving away from it at a constant speed. Then it collides and slows down. So watch what this looks like. It's moving away at a constant speed and then collides and slows down. What do you notice about those two lines the way that I drew them?
They're both straight.
They're both straight, which means that the speed is constant. And how do they differ?
Is that one for one flat?
No. Flat would indicate not moving.
One is a steeper slope.
Good. This one's steeper, which means it was faster, and then it collided and did what? Slowed down.
Yeah.
Cool? Now, the other card is seen by the other sensor. The other card is seen by the other sensor. So what's interesting about this one is that it's not moving. Sorry, that one's supposed to be flat. It's not moving, and then when the other card hits it, it starts moving toward the sensor, which means its position is going to be decreasing. So, I know, I'm giving you like a kind of a framework for this, so when you do it, you can compare what you're experiencing to this and see if they match.
Oh.
So this is not supposed to be super crystal clear, just follow along. Okay? Now, this is all fine and dandy, but I want to use the velocity graphs to get the velocity. So let's do cart number 1 again. Cart number 1 is moving at a constant velocity and then hits and slows down to a new constant velocity. So it's moving fast at a constant velocity, then during the collision it slows down to a new constant velocity. Slowed down. Do you see it slow down there?
Yeah.
Okay. What does the red one do? Initially the red one's not even moving, true? So it's not moving, so it has 0 velocity, and then it gets hit, and it drops to some new velocity. Now, this is confusing, because it dropped to a negative velocity even though it's moving to the right. And the reason is that this sensor here, that's picking up the motion of this cart, because it's moving toward this sensor thinks its velocity is negative. Okay? But we're going to use our understanding to say that no, we know that it's positive and it's okay. So far, so good? All right, well, what are you guys going to do with it?
I can't tell the difference between those colors. I'm just drawing it.
So what are you guys going to do? At your station, on a whiteboard, you're going to create the following table.
They are. Yeah. don't know, because I can't see it. Which line is that? Well, I can see the horizontal, that far away, on that screen. That just all looks blocked. Like, unless I really strain my eyes. Well,
I can't even see it.
That's a lot of information.
What's that?
That's a lot of.
colorblindness is.
I don't have
Yeah, me too. Yeah, me too. Should my grandma, my mom.
All right. So here's what you're gonna do. You're gonna run it, get a good trial, make sure that you can get the velocities off your graphs. Okay? So you're going to measure the masses with the triple beam balance. This is what's going to go on a whiteboard, so yes. Okay? So, hold on.